Thank you, Uncle, for the introduction, and thanks to the Science Foundation for inviting me and giving me this opportunity to present my work. So I'm Johannes from Harvard University. I'm working with Trinity Narang in the Narang lab, and I'm going to talk about first principle approaches to strong light-matter coupling, basically a framework which we have developed, or we have been developed over the last years. Also started with Uncle in Hamburg. Okay, so as an introduction, we saw two very nice talks already this morning, also over the week. We saw very nice talks, so I guess I don't have to do much of an introduction why these problems is interesting to us. Nevertheless, I want to just talk a little bit about my point of view. So already Thomas Epperson was talking about, basically he's a pioneer in this new field of laboratory chemistry. And there the idea is that you couple many molecules to an optical cavity, and this is then a collective coupling. So many molecules are coupling collectively to this, usually it's a single cavity mode. And nevertheless, there's also quite the opposite limit, I would say, which can be now achieved in nanoplasmonics, where people look at nano gaps, where they can put now a few molecules, they excite the nanoplasmonic resonance, and then they see strong light-matter coupling down to the few molecule limit. And not only molecules have been explored, but also two-dimensional materials. And in general, we are interested in, or the question we have to ask from the theory side, then how can we predict these changes in not only spectroscopy, but also different materials properties such as chemical reactivity and even superconductivity. So I want to discuss briefly one additional experiment. So this is an experiment which has been performed by Jeremy Baumberg in Cambridge in England. And basically what they do, they have a gold gold interface, and on top there's a gold nanoparticle. And then they can put single molecules or few molecules within these small gaps here. And then usually what is used as a proxy, whether the system is strongly coupled, is what is the so-called rabbi splitting here. And then you see the splitting of this particular here excitation into the lower and the upper polariton branch. And they have shown in this experiment already in 2016 that they can achieve this strong light-matter coupling up to the few molecule limit, even down to the one molecule limit. And yeah, this I don't think I have to explain too much. This is an experiment which Thomas Epperson has described in great detail, and which they have been performing. And the idea is now that the field is now really at a stage where they can change the chemical reactivity and also can change chemical pathways. Yeah, and from the theory side, the question now is, so these systems are rather complicated, so they consist out of electrons, nuclei, and protons. So the question we have to ask ourselves is, how can we describe such systems? And then just to give a brief overview what one could use to describe such systems. So I'm from the electronic structure community. So usually one thinks about methods here to describe, for example, chemistry, but also solid-state systems. Is, for example, density function theory. Also other systems, or other theories can be used, GW or copy cluster, for example. However, those theories usually focus heavily on the quantum mechanical side of the electrons, and the light field is usually either ignored or treated classically, semi-classically. And quite the opposite limit, which is computationally very heavy on the light field side, are methods which are, for example, used in this field of photonic crystals, which solve basically Maxwell's equation in a computationally very heavy fashion, for example, finite different time domain methods and transfer methods. However, if you then look at the matter side, usually this is then just described by an effective model. So if for these strong coupling situations now, light and matter meets kind of on the same footing, so we have to describe both on the same level of theories. And then what comes to mind is then what also was discussed already during these workshops are ideas from quantum optics, for example, effective Hamiltonians such as the Rabi or the Dicke model, which has been discussed, or the James-Cummings model. However, the question is now, if we think about, we want to describe chemical reactivity and really chemistry, then the question is, how can we describe the matter side? How can we describe this just by a few level approximation? So it would be nice if you can just have a method which can describe the chemistry from a first principle side, and also still take into account some part of the quantum effects of the light field. And to this end, recently the community has extended some methods from the electronic structure theory to this regime. One is what I want to talk about a bit more in detail today, is the density function theory for quantum electrodynamic resistance, we call QEDFT, but there are also other methods, for example, non-equilibrium Green's functions methods. So this brings me to my outline. First, I want to discuss QEDFT. Then I want to discuss the extension to the time domain, basically linear response theory, to also access excited state properties. Then we want to discuss adding the nuclei. And in the end, I want to finish with our new approach, which is a wave function approach for such systems. First, I want to remind the audience briefly, probably you all know about that, what is density functional theory and how can we think about density functional theory. And then later I want to draw the analogies to what changes if you now consider also the photon field. So DFT is a problem to maybe solve is too strong word, but you have to calculate properties of many interacting electronic systems. And then basically the Hamiltonian can write down like this, and you also have the electron-electron interaction term, which complicates these problems. And then many people think about the solution of these many-body problems in terms of wave functions. However, what is nice with density function theory is that we can think about the solutions in terms of the electron density, which is just a one particle object, so it scales much more nicely in terms of number of particles. And then DFT is all based on this so-called one-to-one correspondence. You can show that there's a one-to-one correspondence for given external potential. There's a unique density which corresponds to this external potential. And in practice, then what we do is that we can exploit this one-to-one correspondence, meaning such that we do not have to perform our calculations in this interacting system, but we can rely on this what is called the Kohn-Sham system. And in this Kohn-Sham system, it's a non-interacting system, so it's in principle at least much easier to solve. However, then in practice, we have to come up with these exchange correlation potentials, which have to be approximated. And on the electronic side, people then use these, for example, LDA or GTA, local density approximations. But there's also extensions to that. Okay, so the question is now, what changes if you also consider the photon field? So first of all, if you think about a Hamiltonian picture, so we have to extend our Hamiltonian. And this particular Hamiltonian, which I write down here, is a general Hamiltonian for interacting electrons with photon modes. It's written down in the Coulomb gauge. I have transformed, starting from minimal coupling, I have transformed from the so-called momentum gauge, where we have the P dot A coupling, to the length gauge, which is connected by this power Roulette-Zener transformation. And I've performed the dipole approximation here already. So basically what we are here left with is this photonic Hamiltonian here, where we have this Q. Basically the photon modes are described by harmonic oscillators, and Q is the displacement of these harmonic oscillators. And Q in the end corresponds in this gauge to the electric displacement field, which is connected to the electric field. And this electric displacement field that then couples, because it's a dipole approximation, to the dipole moment of the system. So we have this D, or Q in this case, times R coupling. However, we also have an additional term, which is a self-interacting term of the dipole moment, which is called the R squared term. It's a dipole self-interaction in a sense. And this is kind of in the analogy of the A squared term in the length gauge. However, both are not equivalent. Nevertheless, in many calculations, what one sees in literature, both are often neglected. And nevertheless, we include it here in our formulation. Okay, so if we have set up the problem, we can think about density functionalizing.
So wait, I'm sorry, can I ask a low-level technical question? Because you said that the R squared was not equivalent to the A squared. Now, I would have thought that if I adopt a different gauge, not the Coulomb gauge, but the radiation gauge, then I would go through all this and I would wind up with something with no R squared and with an A squared. And the choice between them is just the gauge transformation. Is that right, or have I missed something?
I'm not so familiar actually.
Okay, all right, then we'll discuss it later.
Maybe we should discuss it later.
Okay, sorry to hold you up. Yeah.
Okay.
How important is it to go to use this Powell transformation? So you can probably also do calculations in the other gauge.
Yes.
Yeah.
So this I will come to. So why we choose this particular gauge is then because we can set up a density functional theory where the density is our basic variable. If we would be in the P dot A gauge, then we would have to go to current density functional theory. Then on the meta side, the current would be the basic variable. And the nice thing about DFT is that if we set up a density function theory, we can use all functionals from traditional density function theory on the electronic side. And in contrast, current density function theory is much less developed. Okay, is there more discussion? Okay, so I already touched like how we can set up. Basically, what we have now to do to extend a density function theory to also include photons is that we have to extend the set of basic variables, or the set of basic variables. In this case, now we get a set. On the electronic side, again, we can choose the electron density. However, also for the photon side, we have to choose a variable, and in this case, we can choose the electric displacement field. So basically these Q alphas here, which is the mode-resolved electric displacement field, can be chosen as the basic variable. And then formally, similarly to normal DFT, we can set up this one-to-one corresponds between the set, in this case, of internal variables to a set of external variables. And this set of external variables, then we can, or this one-to-one corresponds, then again, we can exploit to set up this concharm system, such that in the end, we have to solve effectively non-interacting equations, which are more easy to solve. Nevertheless, we also have the price which we have to pay is that we have to think about these mean field exchange correlation potentials in this case. And if we, in this case, these exchange correlation potentials are due to the, describing the electronic dynamics due to the electron-photon interaction. And if we neglect any exchange correlation potentials, then basically what we are left, if we only include the mean field term, then what we are left is basically coupling Schrödinger equation with Maxwell's equation. So we've did a semi-classical approximation. So the question now is how can we include quantum effects into our QEDFT scheme? How can we go beyond Maxwell's equation? And what one can do is that one can connect to many-body perturbation theory. So one can exploit the connection between the electron density to the interacting Green's function, which and then correspondingly to the concharm's Green's function. And then one has to choose a self-energy. Here we use a GW naught type approximation. And the interaction which we here include is the lowest order diagram, which is a second order in the electron-photon coupling strength. And again, here we find that we have two terms. So we have this term here, which includes the photon Green's function, which describes the explicit electron-photon interaction. And additionally, we have this beta function here, which describes this electron self-interaction. And effectively, what we have done is that we have included one photon processes, such as photon emission or photon absorption. However, the part which we have neglected are retardation effects. And in terms of computational complexity, is that this scheme is now comparable to Hartree-Fock or to electronic OEP, and in a sense also to what people in electronic density function theory are doing if they are calculating hybrid functionals. So it's at the same level of theory. So we also looked at how it performs in practice. So this is the first time I want to introduce now a molecule. So basically, we looked at an acetylene molecule in optical cavity coupled to a single photon mode. And we were wondering ourselves what happens or how is the electron density changed if we put now this acetylene molecule inside the optical cavity and these changes then with respect to outside the optical cavity. And in DFT, one straightforward observable is the electron density, so we can construct the electron density. We see the electron density has this two organic ring-like structure. And if we construct the difference in the electron densities, then we see that there indeed are changes. So due to the coupling to the electron-photon interaction, in strong coupling, we see that the electron density is reshuffled. And we see here, for this particular case, the electron density is accumulated outside of this first organic ring here. And we see also here a depletion of the electron density between the atoms.
So this is in vacuum?
This is in vacuum.
And what is the coupling strength that is issued?
So the coupling strength, we have chosen a specific value. In this case, it's, if I remember correctly, it's a strong coupling regime. So it's kind of 0.1 corresponding of the, if you would calculate a Rabi splitting in the absorption spectrum, it would correspond to a splitting of 10%.
Do you introduce a coupling constant, or it just comes in through the size of the cavity?
So this is, you can do it either way. So if you choose a specific size, then this gives us a specific volume in the end of that mode, then this dictates our coupling strength. Okay, and since we calculate in this density function theory formulation, we have not only access to electronic observables, but also photonic observables. So what we can also construct, for example, is then the number of virtual photons which are excited in the ground state. And we can not only calculate purely electronic or purely photonic observables, but we can now also think about new type of observables, kind of correlated observables. We can even think about a new type of spectroscopy. And we can calculate observables, for example, such like this one, which is effectively the probability to measuring the electron density and the absorption of a photon at equal times for if the system is in the ground state. And this correlated observables gives us spatially resolved properties, or say something about the spatially resolved light-matter interaction. So we see here different phases due to the electric field, and we get this observable spatially resolved. So we have now a kind of new a tool which gives us access to new types of observables which haven't been much explored in the past. So far I've talked about ground state properties, but we can also calculate excited state properties, and if light and matter meets, then typically one is interested in excited state properties. So the question is, how can we access excited state properties? And just to go back to a normal density function theory, TDDFT, what people very often do is they use linear response theory. And in linear response, what you have an external perturbation, and the external perturbation then is connected via the response function to the response of the system. So the electrons respond with extensively response, and you have these response functions. And if you have information about the response function, then you know how the system acts to a general arbitrary external perturbation. And the question now is, what changes if we put the system inside a cavity? So first of all, now we have two different subsystems. So we have the electrons and the photons. So if we can choose to perturb either one. So we can perturb either the electrons, and then we have this electronic response function again, which is connected to the density response. However, what we can also do is that we can perturb the photon and ask ourselves what is the response of the electrons. And then we get a new type of response function, which is these electron-photon response functions. And in practice, what we do is we connect then again the many-body response functions to the Conchamp response function, and then you get these Dyson-type equations. And again, we have these kernels, those kernel functions which include the exchange correlation potential, which have to be approximated. And what we can do to solve this efficiently is we can go to the frequency domain, and then we can reformulate the problem of linear response in terms of an eigenvalue equation. So in quantum chemistry, this is known as also the Casita equation. If one looks at electronic properties, then what one finds is one gets this specific matrix here, which has a matter block on the diagonals, has a matter block and a photon block, and then one gets these V and W blocks, which couple the electron and photon subsystems. And the eigenvalues of this matrix are the poles of the response function, or the squared of the poles of the response function. And if we had the exact, or if we could access the exact Conchamp potential, then we would have access to the exact many-body excitation energies. So I just briefly want to show you how this looks in practice. So one straightforward thing one can do is one can calculate spectra again. One can, for example, calculate absorption spectra. And here we look at a benzene molecule coupled to a single photon mode. Now this is in the so-called electronic strong coupling regime. So we have here this particular HOMO-LUMO transition around 7 electron volts. And now we tune the optical cavity in resonance to this specific mode here. And then we see if we increase the electron-photon coupling strength, or if we reduce the volume of the cavity mode, then we see an increase in the Rabi splitting. So we can reproduce the Rabi splitting also in our spectra. And so the result which I showed just now was for a single photon mode, but what we can also do is we can now couple the systems to many photon modes. In this particular case, I coupled these benzene molecules to 80,000 photon modes. Basically, we sample a one-dimensional cavity. These 80,000 cavity modes now introduce an additional 80,000 poles to our system. And now what is interesting is if we plot these poles next to each other with their corresponding transition dipole moments, then we see that our peaks, which are in standard electronic density function theory, you only get one peak, one pole in the response function. Now we get many poles, and these many poles then effectively basically lead to a broadening of these peaks. So if we plot the poles next to each other, then we already get a broadened peaks. And the broadening of these peaks then corresponds to the lifetime of our excitations. So basically now we have a way to calculate lifetimes from first principle methods. And this was a benchmark calculation, so this was to closely resample a free space case. And in free space also the Wigner-Weisskopf theory can be used. Which is an analytic approximation, or which is an analytic formula, and this is plotted here in the gray, on the gray, and then we see that our numerical prediction corresponds very closely to this analytical equation of the Wigner-Weisskopf theory. And we can use linear response theory to also study problems from photochemistry in optical cavities. And in photochemistry, also Thomas Epperson was talking a little bit about it. So for example, so people usually describe photochemistry in terms of potential energy surfaces. And this is one specific potential energy surface I took from the web, where one has a ground state potential energy surface, a photochemical, so photon comes in, then excites this wave packet, to the second potential energy surface, and then one has adiabatic relaxation processes, usually through such either conical intersections or avoided crossings, and then the system has a certain probability to go in back to the ground state potential energy surface, and it can, however, end up also in metastable states, for example, these trons or cis configurations. And then the question is, how does this picture changes under strong light matter coupling? And first of all, already the concept of potential energy surfaces is basically tied to an electron-nuclear problem. And then what the community has found is that depending on how you tune the cavity resonance, or what is the excitation, or what is the frequency of the cavity mode, we can either classify the photons more to the nuclei or more to the electrons. And if one groups the nuclei and the photons, then you can think about this. This is very favorable for the cases of vibration and strong coupling. And basically one has electrons and classical nuclei and photons. And then one finds this cavity Born-Oppenheim approximation where the potential energy surfaces now are again electronic energies. And for photochemical processes, it's more favorable to work in the electronic strong coupling limit. Here then the photons mode is in resonance to an electronic excitation. Then it's favorable to tune to group the electrons and photons together, and then the nuclei are treated classically. And in this case, one finds not anymore just electronic surfaces, but polaritonic surfaces. And these are now dressed surfaces. And for this, so we can now use the linear response formalism I've just introduced to calculate finite systems. So as again, proof of concept, we've looked at this formaldehyde molecule here, where we calculate the potential energy surfaces using density function theory along the CO stretching mode here. So the CO distance is here plotted in X, and over the energies. And then we find that the ground state is very harmonic. And so in the excited state, we find this double weld structure. And if you think about a photochemical process, then to the second potential energy surface, the system will be excited here, and then it will adiabatically relax. And we'll have certain probabilities going out to the left or to the right, depending on these energy differences here. Now, if we couple these potential energy surfaces strongly to an optical cavity, so this is a zoom here to this conical intersection here. You see there's a gap of around 0.3 or 0.4.
Is this vibrational or?
No, this is electronic strong coupling. Yeah. And so this is outside the cavity actually on the left-hand side. And now if we tune the cavity in resonance in between these two surfaces here, so we choose the cavity frequency around, or basically at 8.71. What we see is a strong hybridization. So first of all, if we introduce the photon mode, then we get an additional pole in our response function. So we get an additional potential energy surface. And this additional potential energy surface can hybridize with the states which are already in the system. And then in this particular case, we see that the avoided crossing is basically closed. And the left surface here strongly hybridizes with the right surface. And now we have kind of different parameters which we can tune, at least from the theory side. What we can do is we can choose different cavity frequencies, but also different coupling strength. And if we increase the coupling strength here and choose a lower cavity frequency, then we see that we can even completely quench the right double weld structure, the right minima here, minimum on the right-hand side, and are only left in this here in the lower potential surface with just one minima. And then again, if you think about these photochemical reactions before, where we had different probabilities, either going to the left or to the right, here we only have one minima, so basically the chemical reaction will always go through the left channel here. And we also have access to a bit more involved quantities. So, for example, the transition density, which is also a proxy for the light matter interaction strength, or how strongly the light field can couple to the system. And if we look at the first HOMO-LUMO excitation here, outside the cavity, then we see this particular transition density, which looks a little bit like a racing car here. And if we now put the system into optical cavity and couple it strongly, we see the splitting in the spectra into the lower and upper polariton. You can also look how the transition densities actually are changed. And we say that there are, in fact, changes which are non-trivial. And in particular, now if we go to much stronger coupling, then we see that these changes in transition densities are beyond a simple 2-level or 3-level approximation. And there's really many states, also from higher lying excitation, which are mixed in to these transition densities. To explain these. Okay, so Thomas Epperson was already saying that the future in this field is in the field of vibrational strong coupling. So I also want to discuss a little bit on vibrational strong coupling. So the motivation I already brought up. So the question now is, if the photons strongly couple to the nuclei, how can we describe such system also from a first principle formalism? And then what we thought about is that we can again expand our set of basic variables. Now we not only have electrons and photons, but also quantity then, which is a measure for the nuclei. And as an internal variable for the nuclei here, we choose the center of mass motion of a specific nuclei species. And additionally, we also have to introduce an external variable, which is a force then acting on the nuclei. And again, we can set up a similar corresponding one-to-one corresponds, which then can be exploited to set up a conform system again. And additionally, now we get even more involved than mean field exchange correlation potentials, which now also describe the nuclei-photon coupling, but also the electron-nuclei coupling. And that this works, or that we can actually perform some simulations, is that we have looked at, again, at a proof of concept calculation here, in this case for a CO2 molecule, which has two infrared active modes here, one at around 800, one at around 2400. And these two modes can be strongly coupled to an optical cavity. And what we use here is our formalism. We use a time-dependent run. This is a time-dependent linear response run. For the nuclei, we use the simplest approximation we could start off, which is basically using Ehrenfest dynamics for the nuclei. And in practice, we have to propagate for very long times because of the nuclear length scale, time scale is very slow. So we have to propagate up to 5 picoseconds. And then we record the dipole moment. The Fourier transform then of the dipole moment gives us infrared spectrum. And again, we see here that we can reproduce the Rabi splitting. So we actually see the splitting into the lower and upper polaritons. We also looked at finite temperature effects. So how we can describe finite temperature is that we put initial velocities on the nuclei. And for this CO2 molecule, then it's interesting because the molecule starts to spin. And in this particular case, we initialized the molecule at t equals 0, such that the dipole moment of the excitation and the cavity polarization is aligned. And then since the molecule is spinning during our run, this overlap is changing. And so effectively, we find a time-dependent interaction strength of the electron-photon coupling strength. And then this is also what one sees. So before we had these these two sharp peaks, and now we see a broad band of peaks, which basically sample different electron-photon interaction strengths. And so we've looked at this for, using our proof of concept calculation, we are now really going at a level where we can tackle problems which have been measured in experiments. So we took the system which Thomas Epperson was discussing already, this TBA system where we have the silicon carbon, where the system has a silicon carbon bond, and then there's a fluor atom attacking. And then the chemical reaction is such that this silicon carbon bond is breaking, and the fluoride is binding to the silicon subgroup. And so this is, I have to say, this is still a work in progress. So we started to do these calculations. And nevertheless, I wanted to share some first insights with you. So in the experiments, as Thomas was discussing, is they see basically whether the system is outside the cavity or whether the system is in off resonant, as the cavity is detuned, and they don't see changes in the chemical reactivity. Only they see changes in chemical reactivity if the system is tuned in resonance. And then now we can use the approach which I just outlined for vibrational strong coupling. So this is a collaboration with Uncle Rubio in Hamburg. And so we look at these systems in gas phase, so we don't include the solvent yet. So this is also what we should think about, how important the solvent really is. And we sample different trajectories inside and outside the cavity, inside with strong coupling and basically with no coupling. And as also Thomas Epperson was already mentioning, that it seems to be that for just random initial conditions, not every initial condition leads to the outcome of the chemical reaction. So this bond here is not always breaking. And this we also see. So actually most of our trajectories which we calculate do not reproduce the reaction mechanism. However, a couple of them does. So it's around of the order of 10% does that. So so we've successfully are able to reproduce the reaction mechanism, first of all, outside the cavity. What we also have shown is that we also find that many of these trajectories also do not seem to change too much inside the cavity. However, we also see that some of these trajectories do change, and yeah, it seems to be that there might be a stiffening of this silicon-carbon bond due to the light-matter interaction strength. And but yeah, this is first of all also depending on initial conditions, not only on the initial velocities of the nuclei, but also of how the photon mode is initialized. And yeah, we have to get more statistics also to get then a thermodynamical picture, which Thomas Epperson was outlining. Yes. Okay. And I think I have a little bit more time. So just briefly, I want to mention a recent approach which we had. So the idea here was, so if one uses density functional theory, then the question is always how does one find these functionals? And one has straightforward access to the electron density. However, it's not always clear how one can calculate functionals in practice. And then we thought we can connect to other methods from quantum chemistry, in particular here to the Hartwig-Fock method, where one calculates a wave function, which is a physical object in this sense. And then maybe we can use these wave functions to come up with new functionals, new type of functionals. And this particular case, we work here in the length gauge, so we work on the P dot A coupling strength, in the P dot A gauge, and we exactly treat the A square term actually, so we renormalize the photons, the photon modes, and we, on top of that, then we include one photon excitations in a sense in a MP2 line, similar as the MP2, which is the Müller-Placid perturbation theory used in quantum chemistry. And I just want to briefly show that this approach seems to be rather accurate so here we looked at 2-level systems, 3-level systems, 4-level systems, also with many photon modes, so up to 50 photon modes. And if we look at the ground state, then we see that a simple perturbative approach, which is just including the A square term as well as the P dot A term perturbatively, seems to fail in the very high. So this is basically already the ultra-strong coupling regime fails. And in particular for the excited state, this is the first excited state, the perturbative approach is qualitatively wrong after some time, while then our approach is very close to, in this case, we can calculate the numerically exact solution. And what is advantageous now that we have additional observables which can calculate. So for example, we can think about how is the photon mode, or how is the mode function of our photon modes changed due to the interaction of to the atom, in this case to the atom. And then we see the mode function, which are usually just joint functions here, because it's a standard cavity, accumulate these kinks here, which effectively quench the electron-photon coupling at the position of the atom. And yeah, this can be understood because a simple perturbative scheme basically does not well in describing the A dot P term, does not well to describe the A dot P term. However, our approach, due to the exact treatment of the A square term, so this also highlights the importance of the A square term, in particular for strong or very strong coupling, seems to perform much better in this case. And yeah, this brings me then to my summary. So I presented a unified treatment of electron, nuclei, and photons, which now offers new possibilities. I talked about single, many modes, ground state and excited states. We also generalized it to the case of nuclear motion, so we can now really study or tackle these problems in vibrational strong coupling. And yeah, the ultimate goal also from the theory side, and probably as Thomas Epperson was also mentioning, that the reaction mechanism is different for different chemical reactions, or they change. And I would say there's still an open question on how exactly, or what is the underlying microscopic explanation on how are these transition states under strong light matter coupling changed. And we hope that we can answer some of these questions with this method. And yeah, in future I also want to extend to periodic systems, two-dimensional materials, to also think about how the quantum, how properties for quantum materials are changed. And also one could think about structured photon bath and yeah, other interesting things. And in the end, I want to also acknowledge people involved in this work. So from the Narang lab, Priya Narang, and also Nick Rivera in particular, and then from Max Planck Institute in Hamburg, Ankel, Michael, and a bunch of other people. And I want to also thank my funding agencies and all of you for your attention.
Thank you, Johannes.
So this last graph that you showed, so is the understanding that if the coupling becomes large, to avoid the energy cost of A square term, the cavity develops a node at the position of the emitter. Is that?
Yeah. So if you think about there's a kind of a symmetry in the Hamiltonians of P dot A times A squared, and then you could think about in a low weak coupling regime, mostly the P squared term, so the momentum of the electron is important. However, if you have very strong coupling, then the A squared term becomes important. And this is basically what we also see then if we more accurately describe the A squared term, then also the overall observables or the other overall effects, such as the energies, are more well described. How this then is in case for if one has a much more electronic levels in a real space description has to be seen.
So you assume 2-level transition.
So here we even looked at up to 4 level in the electronic side, and we see that the electronic excitations or the many body energies are well described up to a very high coupling strength.
I'm sorry.
Yeah, go ahead.
In the perturbative line that you're showing here, basically there is no A squared term at all.
No, the A squared term is included perturbatively,
Okay, I see.
as well as the P dot A term.
Okay.
And in our approach, we include the A squared term exactly,
Okay.
so we renormalize the photon frequency, and this already seems to help a lot in these regimes.
So I'm not an expert on this by any means, so maybe it's a really naive question, but does this method address the issue of photons just leaving the cavity? Is there dissipation in this?
So this we haven't included yet, so this is also one what we want to study next, but in principle it should be possible to also include that. But this is certainly interesting.
One of the graphs he shows is this radiative lifetime. You get a photon, so and how it's leaking out from the mirrors, which is not done.
What could think about describing larger box and then thinking about a cavity in a smaller box and then coupling to also these outside modes, and then
So
one would effectively also.
Conceptually, you can put this in your framework. I don't know. It's not outside. So this Lindblad and all this.
Yes. Yeah.
Okay.
So the Lindblad it's a little bit different. I mean, it's different. We have a density function theory framework, but yeah, there is a way to also connect to Lindblad formulas.
More questions? Or comments? No. If not, we thank Johannes, and then we move to the next topic.